Hello everyone, and a very warm welcome to this explainer. I am absolutely thrilled to have you here today. If you're just starting your journey into physics, you're probably super eager to jump right into the flashy stuff, right? Learning about force, motion, energy, the really dynamic parts of our universe. But, well, before we can do any of that, we absolutely have to tackle the single concept that quietly underpins literally all of it. We're talking about units of measurement. So let's dive right in, shall we?
Okay, I want you to picture a scenario for a second. Imagine you're waiting at a train station, maybe checking your phone, and someone walks up to you and simply says, "The train will arrive in 45." What does that number actually tell you?
Exactly. 45 what? Are we talking minutes, hours, seconds? That single missing word changes absolutely everything about your day. Without it, the number 45 tells you almost nothing. Now take that exact same problem and carry it into a physics lab, an engineering calculation, or, a multi-billion-dollar space mission. In those contexts, an undefined or incorrect unit isn't just confusing, it's downright dangerous. Units are the secret ingredient that makes our numbers actually mean something.
Section 1. What exactly is a unit of measurement? Let's get our definition straight.
Simply put, a unit of measurement is a definite, standardized magnitude of a physical quantity adopted by convention against which all other quantities of that same kind are compared. I know, that sounds a bit textbook, so let's break it down. It basically acts as a reference point. So, when you say a desk is 120 centimeters long, the centimeter is your chosen reference length. The number 120? That just tells you how many times that reference fits into the actual length of the desk.
Now, every single physical measurement follows a very specific structure. We call it the foundational equation of measurement. It looks like this: Q equals N times U. So Q is the physical quantity itself, the N is the numerical value, and U is your chosen unit. The absolutely profound thing about this simple little equation is that if you change the unit, the numerical value changes too. But the physical quantity itself, it doesn't change at all. Think about it like this. A length of 1 meter and a length of 100 centimeters are the exact same physical length, right? Same exact length in the real world, but because we swapped out the unit, we get a totally different number.
Section 2. Fundamental and derived quantities. Let's see how these build on each other. So, you might be wondering, do we just invent a new unit for every single thing we measure? No way! The entire framework of measurement is actually built on a tiny set of base quantities. In the internationally accepted SI system, which, by the way, was established back in 1960 to fix the absolute chaos of everyone using inconsistent measurements, there are exactly 7 of them. We've got length in meters, mass in kilograms, time in seconds, electric current in amperes, thermodynamic temperature in Kelvin, amount of substance in moles, and luminous intensity in candelas. Think of these as the 7 fundamental pillars. Every other measurement in physics is built right on top of them.
And those other things built on top, we call them derived quantities. They're literally just combinations of those 7 base units pieced together by multiplying or dividing them. Let's look at force, for example. The unit of force is the Newton. But that isn't just some random name we picked out of a hat. It directly follows from Newton's second law. Force equals mass times acceleration. Since mass is in kilograms and acceleration is in meters per second squared, 1 Newton is precisely the force that gives a 1 kilogram object an acceleration of 1 meter per second squared. The unit itself is actually encoding the physics. It's like a giant puzzle where all the pieces fit perfectly.
Now, what happens when things get incredibly large? Or, conversely, incredibly small? Well, one of the most practical features of this SI system is its prefix structure. Instead of creating completely new units for tiny things, we just slap a prefix on the front to scale the base unit up or down. So when a physicist talks about a wavelength of 500 nanometers, what they actually mean is 500 times 10 to the power of -9 meters. The little nano prefix handles that massive negative exponent beautifully, so we don't have to write out incredibly cumbersome strings of zeros over and over again. It's a real time saver.
Section 3. Real-life examples of units in physics. Let's take this out of the abstract and into the real world.
I know what you might be thinking. This all sounds like a very dry classroom exercise, but I promise you it is not. Let's apply these units to real-life physics exactly as you'll see them when studying dynamics. Take a car cruising at highway speeds, say 90 kilometers per hour. Now, kilometers per hour is a derived unit of speed, which is great for the dashboard. But remember, the actual physics calculations in dynamics always require SI base units. So before you can plug that speed into a physics equation, you absolutely must convert it. 90 kilometers per hour converts perfectly to 25 meters per second. The actual physical speed hasn't changed one bit, but getting the unit right is the absolutely crucial first step to getting the correct answer.
Okay, here's another real-world example, and trust me, this one confuses students constantly. Think about stepping on a bathroom scale. If the scale reads 60 kilograms, that is your mass. Mass is the actual amount of matter in your body, measured in kilograms. Your weight, however, is a completely different physical quantity. Weight is the gravitational pull, the actual force acting on that mass. And since weight is a force, we measure it in newtons. So a 60-kilogram mass actually has a weight of about 588 newtons here on Earth. They are related for sure, but they are absolutely not the same thing.
Let's look at one more practical example, your household electricity bill. If you look closely, you'll see you're being charged in kilowatt hours, or kWh. Now, as we know, the SI unit of energy is the joule. But a joule is an incredibly small amount of energy for everyday household use. It would make your bill's numbers astronomically huge. So, electrical engineers use kilowatt hours as a much more practical unit for everyday life. But the true beauty of this system is that it still derives straight back to the SI base. 1 kilowatt hour equals exactly 3.6 million joules. So it adapts to everyday needs without ever abandoning that foundational physics framework.
Section 4, Visual Understanding and Verification. Let's talk about a really powerful tool called dimensional analysis.
A lot of times, students treat units as a mere formality. Just a little letter you lazily tack onto the end of your answer. But units are actually a super powerful built-in verification system. Take a look at these notations. Notice the correct standard symbols on the left compared to the misleading ones on the right. Using standard symbols, like writing a capital F equals 10 capital N, is the correct standard language of physics. Writing force is 10 Newton or using a lowercase n is just plain incorrect. And here's the real kicker. If you derive a formula and the units on the left side of the equal sign don't perfectly match the units on the right side, you've made a math error somewhere. It's guaranteed. It's basically like having the answer key right there in the problem.
Section 5. Quick recap. Let's cover the major pitfalls you absolutely need to avoid in your exams.
Let's fire through these top mistakes really quickly. First up, confusing mass in kilograms with weight in newtons. Don't do it. Second, forgetting to convert your units, like kilometers per hour to meters per second, before you start calculating. Third, dropping units mid-calculation. If you do this, you completely lose that built-in checking system we just talked about. Fourth, mixing unit systems. You can't use grams in step 1 and kilograms in step 2. It just won't work. Fifth, ignoring prefix awareness. Always remember, 1 millimeter is absolutely not the same as 1 meter. And finally, the absolute biggest mistake, thinking units are optional in your formulas. Every single symbol in a formula, like V equals U plus AT, carries a unit. And the units of each term must match perfectly. They aren't just labels, they are the physics itself.
Section 6. Practice questions. Let's wrap up with a final thought exercise to really cement what we've learned today. So, I want you to ask yourself this. Can a number in physics be meaningful without a unit? What do you think? Well, the answer is rarely. There are a few tiny exceptions, things like refractive index or strain, which are naturally dimensionless. But for the vast majority of physical quantities, a number without a unit is physically incomplete and completely meaningless. If you take away absolutely nothing else from this explainer, please remember this. In physics, a number and its unit are an inseparable team. Keep them together, use them to check your work, and you will be well on your way to mastering these fundamental concepts. So the next time you look at a physics equation, will you just see a bunch of random numbers, or will you see the perfect, elegant balance of units holding our universe together? Thank you so much for joining me today, and keep exploring.